So now we looked at emission spectra, but all elements also have an absorption spectra. So how do these relate? Well, if you look at this picture, you can see that the emission lines correspond one-to-one with the absorption line. So what's going on is the electrons like to absorb photons that get them from one energy state to another, and only exactly those ones, because they can't take in too much energy, because those would get it to energy states that aren't allowed, and they can't take on too much energy because that wouldn't be enough energy to get up to the next allowed energy state. So the absorption spectra correspond directly with the emission spectra. How do we get an absorption spectra? Well, we shine all the colors. We shine white light on an element in our spectrometer, and then see what wavelengths are missing. So applications of the absorption spectra are that this is the only way we know what stars are made of. We can use this to analyze both stars, our own star, as well as distant planets by figuring out what their spectra looks like and figuring out which lines are missing. We can also use these, as we had before, to figure out Doppler shift because we know where these lines should be. This is a spectra that I took of our own sun in May of 2022. This is actual data looking at a cloud, and here we're going to review a little bit about black bodies, as this is the black body curve from the sun. You can see its peak is roughly in the green, so if anything, our sun is green because that is its peak output. But if we use our equation for black bodies that we learned last chapter, if we have approximating 500 nanometers as where that peak is, I get a number of 5700 Kelvin, which is pretty close to the actual value. So not too bad for a rough calculation. But here in the spectra, you see lots and lots and lots of dips. Those are from all the different absorption spectra from different elements and different molecules. Some of them are for water, some of them are, since I did this in our atmosphere, we have lots of elements in our atmosphere, so some of those dips are due to that. But here we can see very strong dips that correspond to the hydrogen spectra. So these are the hydrogen spectra wavelengths. This is just the marker for 700 and 500, but this is literally the hydrogen spectrum overlaid with our solar spectrum, that you can see very strong dips corresponding to our hydrogen spectra, which is why we know the sun is made of mostly hydrogen. These are the absorption spectra for other stars, including our sun. The sun is a G-class star, and so you can see the spectrum shifts towards the blue and ultraviolet as the star gets hotter and hotter, which is exactly what we talked about with black body radiation. Now we're going to look at the absorption spectrum from two different suns. Our sun is again a G-class star, and Vega is an A-class star. So Vega is much, much hotter than our star, but you can see the classic hydrogen peaks in both stars. So we don't see quite as much of our sun for that last peak because it's already dropped off a little bit. It really doesn't have anything left to lose because we're already coming down in intensity. But you can see that the stars are both made of the same thing.